Hi, my name is Jim Cooper. I'm the Senior Petrochemical Advisor with the American Fuel and Petrochemical Manufacturers. I'm here to talk about why the petrochemical industry is considered critical infrastructure. We make 6 chemicals: ethylene, propylene, butylene, benzene, toluene, and xylene. These 6 materials are the building blocks for all the modern materials that are found in a hospital setting. From the masks that the surgeons are wearing, to the protective gloves, the gowns, the booties, even the draperies, IV bags, the tubing, single-use syringes, all these start with those 6 chemicals. We have to operate 24/7, 365 days a year to enable these materials to go through these supply chains. That's why we're considered critical infrastructure.
We've heard it before. The call is serve. At the turn of the century, Americans were essentially limited to traveling by horse. We answered, producing the gasoline that fueled America's rise to an economic powerhouse. In the 1930s, the Great Depression had the economy reeling. We answered, creating jobs and everyday products that made lives better. In the 1940s, the Axis powers threatened to destroy the free world. We answered, producing the fuel that enabled the Allies' airstrikes. In the 1970s, an energy crisis ground America to a halt. We answered, becoming the most efficient crude refining system in the world. In 2020, the coronavirus came to our shores. We answered, working around the clock to produce the raw materials for the masks, gloves, and sanitizers needed to protect us all. When the next call comes, we'll be right there with you, ready to answer.
Oh, it's beautiful today. I absolutely love to fly. It's my favorite thing to do.
Schneider 76 Whiskey Bravo's airborne.
My name is Michael. I'm the founder of Pilots to the Rescue. The first rescue that I did was back in 2015. Someone took these puppies and threw them on the side of the ditch.
1000 climbing, IDET 976 Whiskey Bravo.
After I rescued those puppies, I realized that there's such a need for rescuing animals.
Today we're going to be rescuing 16 animals, 12 puppies, 4 dogs. North Carolina has a big overcrowded shelter.
They're getting 50 dogs a day, and if you don't get them out, they unfortunately have to euthanize them.
3025 976 Whiskey Bravo.
We can rescue animals in a short period of time.
Yes, Mama, I know. I take care of you. I take care of you.
I'm grateful for the work that the people do in the refining industry. The essential resource that we need is fuel, and I needed to do this mission.
Raise your hand if you never want to do this again. We all want our lives back, but we also want to be safer and smarter tomorrow. America's fuel and petrochemical manufacturers know how to weather storms. We proudly keep essential services running, and we're making the key ingredients for new products, like reusable PPE, advanced testing, and cleaning solutions that help bring us all safely back together. This is how we make progress.
Good morning. My name is Mike LaFond. I'm Director of Industrial Hygiene for Phillips 66 and a member of the AFPM Industrial Hygiene Subcommittee. I want to welcome you to the 2021 National Safety Conference and to this panel sponsored by the subcommittee. Next slide. This morning we have several industry representatives who will be discussing silica hazards and controls when working with refractory. Joining me will be Colin McDaniel from ExxonMobil, who will be discussing refractory controls, and Alex Maple from Marathon and Joe Brown from Diamond Refractory, who will be discussing silica hazard challenges. Next slide. Next slide. I want to kick this off by talking about a project the subcommittee conducted to better understand exposures to crystalline silica, respirable crystalline silica. The idea was to collect and aggregate member company exposure data to silica to look for patterns and trends during refractory work. We were also interested in looking at the role of ventilation to control exposures. Ultimately, we wanted to identify best practices to aid members with managing silica exposures during refractory work. Next slide. When putting the plan together, we considered basic tasks involving refractory work and then grouped them by worker job description and position and type of ventilation used. The goal was to populate each category with member data. As you can see from the chart, that's potentially 32 categories. Before I get into the data, I want to briefly go over the types of ventilations we considered and the tasks performed in each category. Next slide. There were three basic types of ventilation that we considered. Engineered ventilation refers to integrated systems that are designed and validated to ventilate larger spaces. In theory, it's a combination of local exhaust ventilation and general ventilation, but it usually involves dropping large exhaust ducts directly into the workspace to provide localized ventilation. Local exhaust ventilation refers to systems that capture contaminants at the point of generation. In refractory, it may involve a large duct, an exhaust fan, often with a filter sock to capture the dust. General ventilation simply refers to dilution ventilation. So for a confined space, it may involve simply putting a fan on a manway. A concern with general ventilation is that depending on the configuration of the space, it may not be effective if there are pockets or dead spaces. Next slide. There were four basic tasks that we considered. Chipping involved using a pneumatic tool, usually a hand chipper, to remove loose or damaged refractory in preparation for gunning. Mixing fell into two categories. For larger jobs, a rig-mounted mechanical mixer is used. It relies on workers who dump bags of dry refractory into a hopper, other workers who monitor the equipment, and others who act as helpers. It's usually a semi-continuous operation. For smaller jobs, a portable mixer is typically used, where workers make small batches of refractory and apply the refractory by hand. Gunning involves using a hose and nozzle to spray refractory on a prepared surface. This is often an individual who is handling a hose, like you see in the picture here, supported by somebody who trims or trowels the spray material. And lastly, cleanup includes sweeping, shoveling, and filling and dumping buckets or wheelbarrows of chipped refractory. Next slide. As I mentioned earlier, there were potentially 32 categories that we wanted to consider. However, we didn't have enough data to fill all categories, and in a few instances, it made sense to combine categories. So we ended up with 11. The chart shows the final categories and the number of sampling data points that we had in each. Next slide. I do need to mention some challenges with the approach that we took. First, and I think the biggest challenge was this was a retrospective study. We had to accept that ventilation and work practices have been evolving, and they may not been as consistent as we would have liked them to be. For example, if you look at the three pictures in the upper right-hand corner, local exhaust ventilation at a hopper could involve hanging a 4-inch duct above a hopper, or using a larger duct, or even employing a field-crafted hood enclosure. There are also questions about secondary exposures. For example, drag out from empty bags can create dust buildup on the floor, and manual handling of emptied bags after they were used may kick up dust, which adds to exposure. Also, sampling method was a potential concern. Sample overload was common, so samples analyzed by the lab were often parsed or diluted, which in effect raised the detection limit of the sample. Also, information on TWA adjustments and task duration were not always available. So what did the data look like? Next slide. From the box plots, you can see that there was quite a bit of variability within each group. Next slide. When we looked for differences within groups based on ventilation, there were not a lot. So for work involving chipping, it wasn't surprising that ventilation had no statistical impact, given that energy and high velocity of particles generated by a pneumatic tool. Exposures with engineered or general or ventilation, or no ventilation rather, were statistically similar. Cleanup showed no ventilation was better than general ventilation, which may seem counterintuitive. However, on closer review of the data, the no ventilation samples usually involved wet methods, which are very effective in controlling dust. And that would explain the difference there. There was a statistically significant difference with gunning between engineered ventilation, which had lower exposures, and general ventilation. Mechanical mixing results were a bit of a surprise. You'd expect local exhaust ventilation to be the most effective, but I think there were two things that were happening. First, filter socks clog often, starving the exhaust system, so it's likely that periods of heavy use had minimal effective ventilation. And second, general ventilation was much more likely to be effective at clearing secondary exposures from dust buildup on floor and from empty bag handling. Results from hand mixing showed the lowest exposures. This task generally involved very short periods of dry mixing. Next slide. When the data were analyzed to obtain the 95% upper confidence limit, it showed some interesting results. Most notably, the confidence limits were quite high, but that really isn't too surprising given the high variability that we saw in the data. Within the chipping and gunning categories, the OSHA exposure limit was exceeded by a factor of over 50 in some of the subcategories noted, meaning that a respirator with a protection factor greater than 50 would be needed in order to control exposures. Also, despite the use of ventilation, respiratory protection was needed in just about all of the categories except for hand mixing. Next slide. So to summarize here, the exposure data showed high variability, pointing to a need for improved control measures and measures that are consistently effective. Secondary exposures and exhaust system maintenance also need to be considered and assessed. The data indicate that a respirator with a protection factor of 1,000 may be strongly advised when exposures are uncertain and variable. A PAPR is often preferred by workers based on experience. And lastly, it's important to pay attention to the type of sampling and the sampling techniques, just making sure that the equipment is used properly and that samples are not being overloaded. So now I'd like to hand off the discussion to Colin McDaniel. Colin?
Thanks, Mike. So hello, everyone. My name is Colin McDaniel, and I'm an industrial hygienist with about 13 years of working experience in kind of the oil and gas industry. I'm currently an industrial hygienist with ExxonMobil manufacturing facilities here in Baton Rouge, Louisiana. You can move on to the next slide. Okay, so Mike has done a really good job of providing a kind of general overview of the data, and that data is what helps to support or justify the need to protect our workers who perform refractory application as well as removal activities in our industry. What I want to take a few minutes to focus a little bit more on is some of the common, and in some cases not so common, control options that are available for us whenever workers are performing refractory work activities in our facilities. Okay, so when talking a little bit about the controls, for those of you who have ever had any real dealings with industrial hygiene or know about the industrial hygiene profession, one of the things that you'll know is that, you know, whether it's a chemical hazard, a physical hazard, or a biological hazard, whenever possible, you want to make sure that you use the hierarchy of controls. And for refractory materials that contain respirocrystalline silica, there's no exception to this rule when it comes to that. So first we ask ourselves, number one, can we eliminate or substitute the hazard? So you see there are some options for doing that, and we'll discuss that a little bit later in the slide deck. And secondly, engineering controls. There's different engineering control technology out there. Can some of that ventilation, especially ventilation controls, be implemented into our refractory processes that we have today? And then administrative controls. So can we use worker rotation options to reduce exposure to one individual employee and maybe spread out some of that exposure? potential exposure. And then finally, we have PPE, and that should always be used as kind of a last line of defense. But unfortunately, we understand that because of the nature of refractory materials, the light and airy nature of the dust, it's a lot more difficult to control than perhaps maybe chemical vapors or welding fumes. And so we'll talk a little bit about some of those challenges in a minute. Next slide. Okay. So now let's talk about some of the more common types of engineering controls. Mike's already touched on dilution ventilation a little bit, and this is a primary method of controlling the hazard. One of the things that we do see across the industry, or even from one job to the next, or you may have inconsistent application of dilution ventilation in some of our vessels or work areas. And for the reasons that I just mentioned, just really the nature of the material or refractory material itself. So we do see that there are some pros associated with using dilution ventilation. You're pumping a large volume of air into a vessel and then diluting the hazard and then removing it from the vessel and capturing it in a filter sock or a cyclone, some type of capture mechanism. And so this can allow for simultaneous work activities going on if you use effectively use or manage dilution ventilation as part of your project. So, so that is still an option. Okay, next slide. Here's another engineering control that's it's rather kind of uncommon type of engineering control that's out there for refractory material, but it's high pressure water demolition. And so essentially you're using high pressure water to cut refractory material. And we've seen that in some cases it can be 10 to 100 times faster than a traditional methods. Some of the cons associated with it are this is a large piece of equipment that has to be put in certain applications. You won't be able to get equipment into a vessel to actually cut the refractory material. So it certainly has to be a very unique application to use a device like this, and we'll talk about some of this in a little bit more detail on the next slide. Okay, so let's move on. Okay, so again, this is just a little bit more detail. You see that the forklift actually brought this carriage in that has these high pressure nozzles, and it actually cut out a pretty large section in a very short time period. It looks like 15 minutes. They were able to remove a large section of refractory. From a planning standpoint, you'll want to make sure that if from a planning standpoint, you consider some of the mud and debris that builds up afterwards. This is a wet process, so you'll have to remove water from the process after the cuts are made in the refractory and the refractory is demoed. Next slide. So again, controlling the hazard at the source. Mike mentioned local exhaust ventilation. Here's another technology. It's a chipping machine that has a hose attached to it. Again, we've tested a few of these at some of our facilities on much smaller kind of scale projects. We haven't done a lot of demoing with this type of equipment on a larger scale type of projects. But we have seen, some positive feedback from the use of a chipper with a hose connected to it. And so again, this is just another option that is out there that might potentially allow you to use a chipper and control the dust at the generation point. So next slide. So from an engineering control standpoint, the mixing hooch, we all know that, from the mixing operations have the potential to produce a very dusty environment in terms of refractory material generation. So the design of those hoods can be very important, the way that they're designed. So if you have the ability to redesign your hoods or work with your planning team, your ventilation specialist kind of on the front end to ensure that you are getting the best capture possible kind of on the front end, you may be able to reduce exposure at the end of the day. So there's this particular example that you're looking at here. You see initial setup. It's got a hopper. The bag is being broken, downdraft. and you're still seeing that dust is being generated and released into the work environment. With a few modifications to this design, later you see that you have a hood on the right, still has a downdraft, but any dust that's going up is going through a duct and moving out of the worker's breathing zone. So the redesign was effective in reducing exposure to the employee. Next slide. So finally, we talk a little bit about elimination or substitution. There are some options to use lower crystalline silica containing materials. So studies or field tests have shown that have yielded kind of mixed results in terms of kind of use of these products. And again, maybe it's just simply that we haven't tested it enough in a clean environment. There have been some contamination concerns where we've seen higher than expected levels with this material, but it could be for some of these reasons that you see on the screen here. You're unable to isolate the mixing environment. Each panel is subject to dust from the previous mix, and those types of factors could be influencing kind of the higher results that we may see when using some of these products. But nevertheless, this is an option that you may want to work with your sites and consider kind of using in the future. Next slide. So finally, from a PPE standpoint, we all know there are some very dusty refractory work activities that take place, whether it's chipping, whether it's mixing application processes. A lot of these can potentially drive workers to the use of a higher level of respiratory protection for these types of jobs. So this is one of the things that you just want to make sure that you consider as you're kind of going through your planning and from a monitoring standpoint, that you take that into account, especially with the reduced PL and occupational exposure limit that some sites now have in place at their facilities. So the consideration for the appropriate type of respiratory protection should always be put at the forefront. All right, next slide. Okay, next we'll have kind of Alex and Joe talking a little bit about some of the challenges in the refractory silica world. So,
thanks, Colin. My name is Alex Maple. I'm with Marathon Petroleum. I'm a CIH, Certified Industrial Hygienist, and I've been with the company for about 14 years.
My name is Joe Brown. I'm the safety manager out here at the Marathon Garyville Refinery for Diamond Refractory Services.
Next slide. So ultimately, we've had the first presenter kind of discussed and reviewed some statistics around different types of exposure controls, and Colin, spoke about some of the engineering reviews, the systems design changes, things like that. So we wanted to kind of broadly look at a partnership that we had, and knowing some of the industry challenges that are out there between in the petrochemical and refining industry, and I have illustrated as some of these. You've got PPE, the various mixing machinery, the dust containment, the housekeeping and job design / ergonomics. Next slide. It gets more intricate as you're trying to deal with dust containment, and you can have something very intricate, kind of as exampled here. Next slide. And about 99% of our struggles are, with machinery similar to this one, on the grounds that it's a mixing hopper for larger scale operations, and for us, it tilts both directions, but it's kind of the universal tool. But there's also, on the right is pictured a similar device with a local exhaust ventilation system integrated into it. Has a smaller opening. Industry is starting to catch up and starting to see some of these different modified systems in place. Next slide. So ultimately, Marathon Petroleum at the Garyville Refinery here in Louisiana, we partnered with our refractory services contractor, Diamond Refractory, and Joe and I kind of, looking at our struggles as an industry and at the site level. We figured out that we wanted to do better in terms of exposure prevention.
And some of the whys, is a joint desire to improve the performance and efficiency for our workers and their health, elevate their exposure monitoring results as an industry segment, respirable particles and respirable silica, exposure and health effects to employees, the PPE consistency, variability in enclosure designs and in locations for setup, secondary challenges, carbon monoxide, and being consistent performance issues for other contractors working at the facility. Next slide. Some of the activities we perform out here at the Garyville site is chipping of concrete, grout, cement structures, cutting and installing refractory bricks, mixing grout, small scale bucket mixing and power tool, large scale mixing machine, industrial mixing station, gunite rig, pneumatic tool operation, and applying semi-dry aggregate. Next slide.
So some of the challenges that we had overall for exposure improvement or exposure prevention was centered around, we noticed, working with the various contractors that did work with Refractory, that there's a understanding the differences between site-specific implementation plan versus, the overall corporate policy. Understanding the differences of how ventilation is configured makes a big difference. Duct diameters, capture velocity, just the understanding the core equipment operation. Some of these mixing hoppers, they tilt both directions. Others, they don't. They tip the same way where the mixer operator stands, or where the helper has to provide access. Sometimes it's a small little mixer, kind of like a bread mixer. Access to equipment, getting a HEPA filter is, not the same as getting a generic household filter. Housekeeping, what am I going to do with all these spent empty bags that have accumulated from all the mixing activity? All those things, are struggles. And the last one is we were coming up with engineering controls or designs, modifications, but if the employee doesn't buy in, if the individual doing the work doesn't buy in, it's really difficult. You have anything you want to add to that?
No, I think you hit everything right there, Alex.
All right, next slide. So ultimately, we had a lot of first attempts at learning, and funny way of saying is a lot of trial and error moments. And it took a lot of brainstorming, watching, doing a lot of air sampling, and basically got visual observations to get a go no go feel. But I'm going to let Joe talk about some of the overall results we got at the end.
So there's numerous trial and error moments while we were here and partnering with Marathon. We developed several different types of hoods, and finally came to the realization that we got a trailer, closed-in trailer, designed it, put in a negative air machine, a hood. It's reusable, so it reduces time on having to have a scaffold built with a hooch, reduces the exposure down to half-face respirator, air monitoring, personal and area. It's appreciation for a technique. It's consistent ventilation design. It's improved ergonomics and material storage. We've eliminated the CO hazard. We have a washable water hose on the inside, and it also helps with the heat stress mitigation along with cost savings passed along to Marathon.
Next slide.
So this is our mobile trailer here. It's all wired 3-phase, so we can be on one side of the plant, have it plugged in, utilizing it. And if we're needed for another job on the other side of the plant, we unplug, mobilize to the other side of the plant, then we're back mixing and working. Next slide. So here you can take a look a little bit in the trailer. What we've done, we've put what you call butcher curtains to help keep that dust within the confines of the hood. And if you look the middle slide, you can see the slide where it comes to shoot, where it comes out the back of the trailer. Once we've finished mixing, the guys never have to step foot into the trailer. They can put a wheelbarrow by the back. It dumps, comes down through the chute and into the wheelbarrow, and they're off to go apply it. Next slide. You can see here just a few things. We talked about, we've mitigated the heat, so we've put in air condition. It has a double door on the side, so when those double doors are open, the forklift can put in material and slide it up, close the doors, and everything's sealed and within the trailer. Next slide.
So ultimately, we had this, this was a great outcome from our partnership and for exposure improvement or exposure prevention, but also we identified, our partnership kind of looking at what other companies were doing, what other sites were doing. We identified that, we needed a poster of some sort that tied all the site expectations and gave some guidance in terms of controls. So we put together a site expectations and controls matrix poster. We realized the importance of smoke testing local exhaust systems being proposed by contractors. They would want to contain the dust, but ultimately we would verify the effectiveness, very qualitatively with a smoke test tube and be able to, see the potential benefits. It's quick, easy. Substitution with less hazard product. We spoke about it previously. If it's available and it's suitable for the job, give it a shot. Third-party resources are critical in this. We found that some tools are needed by the subcontractors and contract workforce to develop their silica control documentation, especially site-specific documents, like how they're actually going to implement controls on site. Next slide. At this point, I'm going to hand it over back for the moderator.
Thank you very much. Appreciate the presentations from each of our experts on silica. Now we're going to move to the question section of our meeting this morning.